Okay. Okie dokie. All right, so hello everybody. Today we're going to start talking about computational Bayesian statistics. So this is going to be the last in kind of a series on Julia for Economists that I'm doing here at the GSB. I'm Cameron Pfeiffer. I'm a finance PhD student at the University of Oregon, but I've been visiting here at Stanford since October. Yeah, just kind of interrupt me whenever questions show up. And today is going to be about 2 one-hour sections with a 10-minute break in the middle. Okay, so I'm just going to kind of rattle through stuff, and you should follow along if you have kind of a Julia installation and a text editor. Though all of this stuff is available online at this Julia Bootcamp 2022 repo, which I'll put in here actually. Okay, so you can go there and you'll be able to see, links to the recording and links to this lecture note that I'm using here, which is a Jupyter notebook. Okay, so today we're basically going to be going over Bayesian statistics. So some of you may or may not have had some kind of experience with Bayesian statistics. Not everyone does, but it's there, it's common, and it's fun to use. So if this is your first introduction to Bayesian stuff, I will have a very kind of light introduction for you. If this is not your first, then I'll have a little bit more of a complicated thing later on, showing you how to use kind of more complicated and interesting Bayesian tools for kind of applied economics. And I have a nice little auction theory example for you. Okay, so I'm going to go through Bayes rule, conjugate priors, which are really lovely if you have them, probabilistic programming if you don't have conjugate priors, and Markov chain Monte Carlo more generally. And we're just going to kind of note this is like my favorite topic, so I'm like incredibly jazzed to be here. Like this is like a very fun thing for me to do. Sorry, my room is incredibly hot now. All right, so we're going to start here with Bayes rule. So this is like we're going to start with just like the very basic construct of Bayesian statistics. Anytime you see a Bayes talk, it's always going to start with Bayes rule because people forget it. And basically what you have is a statistical identity. So suppose we have a model. So a model here is, it could be like a linear regression type model. That is a model. And it has parameters theta, and this could be a vector, this could be a set, this is whatever. And then you have some set of data x. Both theta and x are probabilistic. Like we're going to think of these as probabilistic quantities. We don't know theta necessarily, right? We're trying to understand our parameters theta, and we believe that x, our data, is drawn randomly from some data generating process parameterized by theta. So once we have this data x in our hand, we can get a better understanding of the types of values theta that might have generated our data x. Okay. So Bayes rule kind of formalizes this for us with this relationship, which is the probability of theta conditional on observing x. This is our posterior distribution, our posterior density, is equal to the probability of x given theta. This term here is referred to as the likelihood. And then this multiplied by the probability, the prior probability of that parameterization theta, and then divide the whole thing by a normalizing constant, the probability of x. Right, so this is just the joint with the theta with the prior marginalized out. Okay, so each of these has names: likelihood, prior, normalizing constant on the bottom, and then on the left-hand side the posterior. This is the thing we want, because once we have the posterior, we can do all kinds of information. We can do all kinds of analyses, right? We want to know, oh, well, does height affect earnings, right? We could think of having like some parameter in here. And x being some data on earnings, and one of the parameters inside of theta is some like coefficient on earnings. We want to know, is it like meaningfully different from 0? What's the shape? What does it actually look like? And so once we have this, we can do all kinds of analyses. All right. So the advantage of having this posterior is that we can make predictions, right? We can understand our data better. So like, for example, one way we could do this is we could predict, if we wanted to predict new data points, like let's say you're doing like kind of a time series thing, you can predict a new data point x prime by just drawing x's from the data parameterized by theta and x. So when you get the posterior distribution for theta, you can just draw random values for x prime from that distribution, and then you have a well-defined density of, like, what's the probability that x prime is going to be above 0.5. That's very easy to do because you can just look at a bunch of random samples. So a lot of like conventionally frequentist methods like OLS are like, I generally consider them, and I think many other people do, as a subset of Bayesian methods with uniform priors. So they're not particularly Bayesian, but you can reframe them as if they were frequentist things with uniform prior, or Bayesian methods with uniform priors. So if you've been running OLS for a long time, you're already a Bayesian. So like, welcome to the cult. So you get to come and party already, and hello. As an example, I'm gonna walk us through this case where we're trying to detect the bias of a coin. So we're playing a game with our annoying friend, and our annoying friend likes to cheat. And the friend just wants to keep flipping a coin for hours and hours and hours. And let's like just assume that we're graduate students and we're trying to like find ways to not write our dissertation. So maybe we're just like flipping these coins forever and ever and ever, so that we don't have to write stuff. So our friend has found a trick coin where the probability of heads may not be 50%. We don't know what this trick coin is, what the probability of this coin turning up heads is, but we want to figure it out, and we get the opportunity to play this game. And at the end of the game, we're going to try and tell our friend what the actual probability of heads was after observing some number of coin flips. And importantly, we're going to be able to tell our friend exactly how uncertain we are about this true probability of the coin flip. And so we're going to do this with a fairly simple little model. So first, anytime you're working in kind of a Bayesian model, you start with priors, right? So in our case, a prior belief is how you as a researcher or an individual feel about whatever the quantity of interest is. So for example, I don't think it's possible at all for him to have found a coin that is always heads or always tails without it having heads on both sides or tails on both sides, right? Let's assume that we're just going to rule this out. So my prior is basically I want a prior that mushes down the tails at 0 and 1 because I know they're incredibly unlikely. And at the same time, I suspect probably because it's very hard to like flip a coin and have it land like 10% of the time on heads, just for physics purposes. I think it's also probably pretty unlikely that it's going to be true probability of this coin is going to be very far from 25% to 75%. It's not going to be in these like end tails. So there happens to be a very good prior for this. And it's called the beta distribution. And so the beta distribution has two parameters, alpha and beta. And it has this density here defined by, the probability of, some quantity x is just equal to, so a continuous value between 0 and 1 has this density. And b here is the beta function, which is just a ratio of gamma functions. And it has this very nice shape to it, which has a probabilistic interpretation, right? The thing we're trying to understand is the probability of a coin flip. So we want something that's between 0 and 1. So I'm going to kind of sketch out a plot of this. And so basically all I'm doing is I'm giving you some random parameters where alpha and beta are both 1, where alpha is 3, beta is 1, alpha is 3, beta is 6, so on and so forth, where they're both 10. And then I'm just going to plot them all together. So I'm going to plot a beta and stick it on my graph and give it a nice little label with the parameterizations I'm using. And so you can see here, this is, these are different types of beta distributions parameterized differently. So for example, this blue line here is flat from 0 to 1. This is technically a uniform prior from 0 to 1. They have equivalent densities. If you do alpha is 3, beta is 1, you get this upward sloping line. If you have, for example, the purple line where they're both 10, where alpha and beta are both 10, you have kind of almost a bell curve shaped distribution that's centered around 50. So when alpha and beta are the same, they tend to be centered at, they are centered at 50. And you can kind of shift them left or right, shift the mode left or right by incrementing alpha or beta disproportionately. Here, let me separate this out a little bit. Okay, so I'm going to use this beta distribution as our prior over P, which is like the probability of my friend's line coin coming up heads. So I'm going to pick alpha and beta such that we believe our coin flip is fair on average, right? So I'm trying to find an alpha and beta such that you know, I don't know which direction to like towards 0 or towards 1 the coin flip is going to tilt. So I want to center it around 0.5. So this happens when alpha is beta. So the higher we set alpha equals beta, the more confident we are that the coin is fair. So alpha equals beta equals infinity means we have like a perfect, you know, we're absolutely certain that the coin flip comes up heads 50% of the time. Okay, so here I'm going to show you, you know, a set of possible priors that I could pick. So I'm going to kind of look at this, and the one that I'm kind of most attracted to here is this orange line here, which is like fairly wide, right? You know, I don't know how, like, you know, I don't know much about trick coins. Like, is it possible that trick coins could have like come up heads 75% of the time? Maybe. I don't know. Like, I don't know how I don't know how these coins are manufactured. So I kind of want to permit some probability in these like kind of like regions where I'm just like, I don't know how you make trick coins. But I also really don't want to have like a lot of mass over at 1, and I don't want to have a lot of mass over at 0 because that's kind of nonsensical. As you know, picking a prior, I'm just going to kind of pick this orange line here. So I'm going to use alpha beta equals 10 because the other ones look a little too precise for me, a little too confident. And I don't know that I have a lot of confidence about what my friend's going to do. Okay. So I'm going to use alpha beta equals 10. Okay, so now we have a prior over the probability that the coin shows up heads on a single flip. So the next thing we need, right, if you remember looking at that at Bayes' rule, there was a thing that we're multiplying by the prior, which is the likelihood. And this is the probability of your data given your parameterization. So there's a couple of good fits for this. The first one is the Bernoulli distribution, right? So this is a single parameter which probability of success, and represents a single trial. So a random draw from a Bernoulli distribution is either 0 or 1, and it is 1 with a probability of whatever the parameter is. The binomial distribution has a single parameter and represents 1 or more trials. Okay, so the binomial is actually the multivariate, or you know, the multi-trial version of Bernoulli's, of the Bernoulli distribution. I'm going to write everything to use the binomial distribution, but you'll see later it ends up basically more or less being the Bernoulli. So I'm gonna draw some random values from the binomial here, just because it's very good at representing coin flips. Okay, so the math function here for the binomial is that we have some success probability P, right? This is the probability of getting a heads. The number of trials or coin flips N. So this is total flips. And then the number of times those flips ended up heads is K. So, and then we get this mass function here, which is pk times 1 minus pk, 1 minus p to the power of n minus k. Okay. It's a very simple mass function. Okay. So I've like very carefully set up this model as a teaching example where I have a beta prior and a binomial likelihood. And this is like a very special thing because it ends up giving you what is called a conjugate prior. So the beta is a conjugate prior to the binomial likelihood. And a conjugate prior is really amazing because there's an analytic form for the posterior, the probability of theta given x, which is awesome because you can just exactly calculate what the result is given your data. Okay. You don't always have conjugate priors, but they're incredibly beautiful to have. And you end up being able to like get rid of a bunch of computation that you normally don't need to do. Bayesian methods can be extremely slow, but if you have a conjugate prior, they are not slow. They're fast. You know, it's basically algebra. So we'll talk more about later in kind of the second section about how not having a conjugate prior is fine, but it's a little slower. Okay. So just to kind of formalize this a little bit more, if a prior distribution p theta is in the same distributional family as the posterior, then the prior and the posterior are conjugate. So distributions are organized by families. A lot of the ones you might know and love are in the exponential family, of which the normal distribution is a member. So you can basically go through and any of these texts, and usually people like smart people have sat down and like done a bunch of math, and so there's all these lists of conjugate priors. And so if you can find those, your example may already have a conjugate prior, or your problem may already have a conjugate prior and a conjugate posterior. And so you don't need to do any of the Markov chain Monte Carlo stuff that you normally do. So it's worth investigating, but you don't always get it. Okay. I'm not going to walk you how to like actually calculate the posterior distributions. That's like for a math class, go do math or just Google it. We're going to use computers here because math is hard. So I'm going to show you this conjugate example, and then we're going to do the like computer goes fast thing later on. All right. So I have this posterior here. So I have a beta prior and a binomial likelihood. The posterior distribution of P, which I'm calling the probability of the heads, given any given coin flip or a set of coin flips X, is equal to beta, where alpha naught is our initial guess for alpha, which I set to be 10. Same thing for beta naught, which is also 10. Then all we do is add up the success. All we do for alpha is add up the successes. And then for beta, we just add up the number of failures. So n is total coin flips here. And then we're just going to subtract out the ones that are successes. And these are all the failures. So if we get a bunch of failures, the new beta parameter, which is also beta, is going to be incremented by the number of failures. Okay, so that's the interpretation here. All right. So let's just write this up. So first I'm going to generate the data. So I'm going to pretend that my friend found this coin, and the coin has a heads probability of 45%. And so we're going to flip the coin 10 times to start with. And 10 times, actually, no, we're not heavily, I'd say not neglected. They are not being neglected because 10 coin flips is fine. Okay, so I'm going to specify the true probability here is 45%. I'm going to set the number of draws to be 10, and then I'm going to draw some coin flips from binomial with a single trial. So this is actually a Bernoulli distribution, but because when you call random on this, it actually gives you the number of total successes, which is a little annoying because I actually want to see each individual coin flip. So when I run this, so now data has my my random draws, and then I'm going to plot out a histogram of my data. So we can see here we've got four tails and 6 heads. Is that right? Yeah. Which is actually a little odd. I would expect that to be like, yeah, here, let me see if I got that right. Yeah. Okay, so this will be fun. All right, so we're going to work with 10, which is a small data set. And when we run the sample, it's pretty volatile, right? So here we're actually getting, 3 successes out of 10, which is roughly consistent with this 45% number. So we'll see as we, as I ramp up the number of fits or the number of coin flips, how much more interesting this becomes. But this is the data we're going to work with for now. So I'm going to set our prior parameters here. Alpha 0 is equal to beta 0 is equal to 10. And then I'm going to write this posterior coin flip function. And all I'm doing here is I'm replicating the p theta given x equation that I just had above for the beta binomial. Alpha, I'm going to increment by the sum of all of the x's. Remember, all the x's are going to be 0 or 1. And then I'm going to add all of the failures to the beta. And then I'm going to return the new alpha and beta, and I'll get these new values here. And so for this one, our new parameters, posterior parameters, are going to be 13 and 17. All right. So I'm going to create my prior distribution. This is the one that I picked. And then the posterior distribution, which is some mixture of my prior distribution and the data. And then I'm going to plot it. So the prior basically had, or the posterior has actually moved towards 0.45, right? This is, the true value is like something like here. We're not super precise about it yet, but we're definitely trending. Like, we've observed some data and we've revised our beliefs about what this probability of the coin flip is, and it's maybe somewhere in this region. We know it's probably not going to be like 0.8. We know that 0.75 has gotten substantially less likely. And so we'll see a little bit more how this scales up as you see more coin flips. So as we get more data, we get a lot more confident about our beliefs. So let's try playing this coin flip game a lot of times and see what happens as we ramp up the number of observations we have. Okay, so oops, there we go. So I don't actually need to rewrite that. So I'm going to save all of my posterior distributions. I'm going to plot my prior, and then I'm going to set up some number of random draws to see. So 1, 10, so random number of coin flips. So 1 coin flip, 10 coin flips, so on and so forth, up to 100,000 coin flips. And then for each of these, I'm going to draw some random data, calculate the posterior given that random data, calculate the posterior using those new parameters. I'm going to save the posteriors into this posteriors array. And then I'm going to plot that distribution so that I can see what they look like. All right. And what we end up seeing is, I can zoom in here a little bit. As we get to 100,000, we get extremely confident about 0.45, 45% as the probability of heads. And there was some like movement around, like this blue one here was, what is that, 100,000? Oh, that one's very interesting. That one looks quite wrong. But anyway, as you see more and more coin flips, you get more and more precise. And so your posterior distribution gets very tight and tall. And so you get a lot more confident about the probability of the heads, which in this case, we've like pretty readily concluded is 45%. After we observe 100,000 coin flips. That's heavily neglecting your dissertation. Okay, so we're going to see what happens to the mean and variance of P, the probability of heads, as we increase the data. So I'm just going to put this in a little summary table. So I'm going to store the, how many trials we observed, what the probability was, the average, the mean of this density, the variance of this density, the alphas and the betas, and then the 5th and 95th percentiles. Okay, so when I run this, you should be able to see all the trials here. The true probability is always 45%. And we can see that as we increase the number of trials going down rows, we ended up getting closer and closer to 45% on the mean. It bounced around a little bit, but we got pretty tight. The variance is basically 0 as we get along, which is about what you'd expect. If I've seen something happen 70,000 times or 1 million times or whatever, I'm extremely confident in the distribution of those things. If I saw somebody flip a 50% coin 30,000 times, or 10 million times, I would know for sure that it's 50%, because I can just count that's, almost always 50-50 on either side. And you can see the posteriors here, they always get higher with the number of total successes. And you can see the percentile. So basically this is telling you, if you were kind of coming at this from a frequentist perspective, these percentiles here basically tell you that the 10% confidence interval for the probability of a heads coming up is between 0.45, 0.448, 0.449, and 0.54. That's how you can interpret this. So that's, the true value is pretty readily within here. And it's a very tight confidence interval. This, on the other hand, is a much wider confidence interval after observing just one coin flip. We don't have a whole lot of information. Okay. So this is like a very nice, super simple example of how you work with conjugate priors. This is like very basic Bayesian statistics. We can't always do this. In fact, I would argue that, like, for most even reasonably complicated models in economics, and even elsewhere, we almost never have conjugate priors. Very rarely do we have conjugate priors, especially now. Like, models have gotten very complicated, and sometimes we're working with very complicated things inside of the likelihood function. And anytime you have that, it ends up being really, really messy. But that's not actually a problem for Bayesian methods. So, we have this thing, you may have heard the word Markov chain Monte Carlo. And I'm going to talk about how we can use Markov chain Monte Carlo to solve things, solve Bayesian models, solve for posteriors when we do not have conjugacy. Okay, so this is not an issue. We just have to do something a little different. And importantly, we have to calculate a numeric posterior and not an analytic one. So that's what happens when you don't have conjugacy. I don't think it's too much of an issue. It's a little bit less fun, but I like numerics. I like spitting out lots of random numbers. So this is Markov chain Monte Carlo is fun for me. Okay, so Markov chain Monte Carlo methods are a family of inference tools that you use to sample parameters from a posterior distribution. You don't know exactly what the posterior distribution is, but asymptotically, you can draw samples from these posterior distributions, and when you collect them all together and like trace them out in a histogram, they follow the true posterior distribution. So you may have heard of things like Metropolis Hastings is a very common one. This is kind of one of the oldest methods. You may have heard of Gibbs sampling, Hamiltonian Monte Carlo, or the no U-turn sampler, commonly referred to as nuts, or slice sampling. All these things are Markov chain Monte Carlo methods. And they tend to be extremely useful and fun and interesting tools. So Markov chain Monte Carlo can work, different methods can work anytime you have a model for which there is a computable likelihood and a computable prior. And this is like a very, very high level tool. So anytime you can compute a likelihood for anything and a prior for anything, you can use my Markov chain Monte Carlo to run inference on that model. That's really important. You may have a lot of models where you have a likelihood. And if you already have a likelihood, you can just throw on a prior and you can get posterior distributions rather than doing maximum likelihood estimation. Because I hate maximum likelihood estimation. I feel like a lot of people don't like maximum likelihood estimation, but we all do it anyway because it's fun and easy. But I just want you to know you don't have to. You don't have to. You can add priors and be a Bayesian, and then you can be cool like Bayesians. Or be cool like Bayesians think Bayesians are cool. So we basically know, I've rewritten Bayes' rule here in a slightly different way. So the posterior here is still on the left, and we still have the likelihood times the prior on the right, but I've dropped the bottom part here, px. This is the normalizing constant. And I've written, instead of equality, I've written this weird squiggly letter, which means proportional to. And the reason for this is that px is really hard to calculate numerically. You need to have, you need to actually know all of the draws ahead of time. You need to be able to you need to be able to calculate this quantity ahead of time before you can calculate this quantity, because you need to integrate out all of the thetas that you observe. Markov chain Monte Carlo, that's just kind of nonsensical, because the idea is that we're just we don't know necessarily what the posterior is, but we know how to draw from it. And so we can't actually usually calculate this as we go along, especially if we don't have conjugacy. This is really hard to calculate without conjugacy. So we're just going to say, okay, well, everything that we draw from this distribution is proportional to this. So we can just kind of basically smush something down and more or less divide by the sum. And we get something that looks like a density. Okay, so we're just going to randomly pluck values of theta. This is from Markov chain Monte Carlo. We have all these very nice stochastic ways of moving from one theta to another theta, and moving around this parameter space in a way that is consistent with the posterior distribution. So that sounds very fuzzy, but I'll show you a graph of what that looks like in just a second. So we're going to start with what is kind of arguably the most basic Markov chain Monte Carlo method, which is called Metropolis Hastings. So I wrote a package that I quite like a year or two ago with some other folks. I think mostly David Widman, who's a Turing developer, called Advanced MH. And if you don't have this, you can go grab it. I'll give you a nice little tour of how to use it. But it's basically just a bunch of reasonably fast, consistent Metropolis Hastings estimators. So the way that Metropolis Hastings works is you need a log joint function, and the log joint function has to return the log likelihood, which is this thing here on the left, plus the log prior. This is, everything you need in a Bayesian model. As long as you can compute this, you can run inference on whatever you want, assuming your model is well behaved. And then you need what is called a transition kernel that proposes a value of theta with some noise. So what you do is you start from some initial sample, like theta 0, right? You just pick something randomly from the prior is usually how it's done. And then Metropolis Hastings basically just adds a little bit of noise to that theta. And then based on the relative probabilities of those two parameterizations, it can sometimes choose to accept the new value or reject the new value and maintain the old one. And so this transition kernel here is the thing that determines how you move from theta to theta prime, some new value. Okay, so I'm going to do my imports here. So I'm going to import advanced MH, distributions.jl. This is so I can use all the fun stuff, all the distributions. I'll do a little bit of linear algebra stuff, mostly just to use the identity matrix a little later on. And then I'm going to use MC chains, which is another package I've spent a lot of time in, which is basically a way of storing plotting using diagnostics on Markov chain Monte Carlo samples. Okay, so this is going to be the data I'm going to work with. So I'm going to generate a set of data from the posterior that we want to estimate. So the true mean is 0, the true variance is 1. And then I'm just going to draw 30 samples. And I'm going to try and understand what later on from the data, what the mean and the variance is. So at the end of this, I want to say I have some confidence level that the mean of the true distribution is 0 and 1. Okay. Now I'm going to define a model. And this is a little bit ugly. And I'll show you a way to make it less ugly later on. But I'm going to define this, let's start with this density function here. So the density function just accepts x, or theta. It will construct the priors in here. I'm doing this just because I want them to be local variables and not global variables. And then it'll check if theta is inside of the support. So the second parameter, this theta here is a vector with 2 values in it. So the first one is the mean, and the mean can be anywhere between negative infinity and positive infinity. That's fine. But the inverse, the variance of a normal distribution is not defined when the variance is 0 or negative, right? If it's non-positive. I mean, it can be 0, but that's kind of meaningless. So actually, yeah. So it's defined when it's 0. I just want to rule out negative values for the variance parameter. And so I check if it's in the support. If it's not in the support, I'm just going to return negative infinity, right? Because the log probability of 0 is a negative infinity. But if it is in the support, I'm going to calculate the log PDF, the log density of the normal distribution parameterized by theta, given my data, right? This is going to be the 30 observations I just calculated up above. I'm going to add the log joint or the log PDF of my prior, and I'm going to call I'm going to pass in the value of the mu. So this is basically what's the probability of the theta I was just given based on my prior. And then I'm going to give in my, I'm going to do the same thing for sigma. So what's the probability of sigma given my prior on that? And then I'm going to return the sum of all of those things because that's a log probability. Okay. It's a nice simple model. And so then we're going to kind of go into like advanced MH land. And so, you know, most of the Markov chain Monte Carlo tools in the Turing world, right? So Turing uses advanced MH. They use something called, we basically require you to provide a model which proxies for something like a log joint. And then a sampler, which is some kind of algorithm to produce samples. It doesn't even necessarily have to be Markov chain Monte Carlo, but it has to be some kind of thing from which you use to generate new samples given your model. And by samples, I mean samples from the posterior distribution.
Cameron, it might be worth emphasizing that this is conceptually pretty different from what you would get out of maximum likelihood. So when you say sampler, you can't say maximum likelihood estimator because they're doing very different things. Right?
Yeah. Like maximum likelihood always gives you a point estimate with uniform priors. So it is the
well, you can have maximum likelihood with non-uniform priors. You can have prior distributions on things. The difference is
that one. If you have priors, then it becomes the MAP estimate, which is the maximum a posteriori, which is also a point estimate. In this case, we're getting slightly more information about our uncertainty around the MAP estimate or the MLE estimate.
Well, the point I was trying to make was that you can do all kinds of different things, but when you do maximum likelihood, you're ultimately just optimizing something. And so what maximum likelihood does, it tells you what is the set of parameters of your distribution that are going to maximize the likelihood of your observations. And you can do that with priors or not priors, but conceptually the reason you're getting a point estimate is because you're just trying to optimize the thing, right? Like these samplers do something conceptually different where they're just drawing from the distribution. And so inevitably you're going to be getting distribution, not just the distribution of your outcomes, but you're going to be drawing, your samples are distributions of the posterior of each parameter.
Yeah, exactly. I'll show you an example of what Shosha's talking about here in just a second. But it's an important point, right? Because we have, I'll show you. I'll defer that into just a second. But so in advanced MH, what we're going to do is use this density model struct here, and this is just a wrapper that goes out that you pass a function to. So density is the function I just wrote, and then I'm going to wrap it in a density model. And then we're going to set up our sampler with a joint multivariate normal. So I have 2 parameters, which means I need to have a distribution that provides 2 new random shocks every time. And so I'm just going to use a multivariate normal with a mean of 0. It's a 2-dimensional transition kernel, and it's going to have the identity matrix as a variance. So this is an isonormal multivariate density transition kernel or proposal kernel. So let's do a small set of samples so you can see what a bad run looks like. So Metropolis Hastings tends to need to run for a very long time because it's a very inefficient sampler. But I'm going to show you kind of what it looks like. So here I'm just going to create a variable called chain. and I'm going to use a function called sample. I'm going to pass model into the first argument, the sampler into the second argument, and then the number of posterior samples I want. The more samples you have, the more detail you'll have about the shape of the posterior, the more likely you'll get a converged chain, which I'll talk about in a second. And then as keyword arguments, I'm going to pass in, the parameter names, and then I'm going to pass in the type of output I want. This is if you want it to be use MCMC chains as the storage material. If you leave this stuff commented out, it'll just give you basically a vector of name tuples, more or less, or structs containing name tuples. But I like working with markup or with MCMC chains, so I'm going to run it. This is very fast because 1,000 samples is not many for advanced MH or for MH in general. And then I can call display chain, and it'll give me some summary statistics of my model. So we can see the number of iterations. We only have one chain in here. We have two parameters, mu and sigma, and then we have the log probability stored separately. So it's hidden because it's not actually a parameter, but it is information about our samples. And then here we can see some information about our posterior distributions, and it's telling me some stuff in here. It's basically saying, oh, you have, your mean is 0.045 with a standard deviation of 0.5. And this is all kind of, this looks fine, right? These look like numbers that tell us something about the posterior. But before you look at numbers from that you got from Markov chain Monte Carlo, you should actually dig into whether or not they're right. And the best way to do this is to plot them out. So here, let me correct that for just a second. Okay. So I'm plotting where the parameters move to in our Markov chain over time. So we can see it started somewhere around, I can't actually tell. It looks like maybe 0.75 or 0.8, something like that. And then it's being given random shocks and it's moving up and down. And you can see these little flat periods here are when we're carrying forward the previous value because we rejected the new one because it was too unlikely given where we just were. So this is very jaggedy. This is not not a good example of representation of our posterior. And when we print it out in a histogram, oops, that is not what I wanted. Okay, so when I print it out in a histogram, you can see we have all these extreme values over here. -4 is what it's guessing for at one point for the true posterior mean, which is I gave it a mean of 1 or a mean of 0. So this should not be it should look a lot smoother than it currently does. And the reason for this is that there's just aren't as many samples as there should be. Because Markov chain or advanced MH MH, Metropolis Hastings, needs a lot of samples. Wow, I did not set any of these to be slides. Okay. All right. So I'm going to resample this with many more samples. So here I'm going to use 1 million draws. Okay, and it'll give me a nice little progress bar. Love the progress bar. So that took 4 seconds to do 1 million samples. And then I'm going to give ourselves some summary statistics here. So now we see a bunch of information here. So the posterior mean for mu is 0.1347, which is a little bit different than our true mean, right? Our true mean was 0, but remember, we only have 30 observations here, right? This is not a lot of data. And the standard deviation of that posterior estimate is 0.166, 0.167. Okay, but let's take a look at what that actually looks like here. I'll point to some of these other diagnostics in just a second. But this is exactly what you want to see after you run some kind of Markov chain Monte Carlo. So this is what is referred to as people refer to this as a caterpillar plot. So the samples that you draw from Markov chain Monte Carlo aren't valid unless your Markov chain has ended up at a stationary distribution. And so when you look at this, is called a trace plots, where you have the parameter value on the y-axis and you have the iteration number on the x-axis. This should look like, there should be no autocorrelation in here. It should look like a stationary distribution. So this is like extremely good. We can see that it's more or less bouncing between, you know, on average, it looks like it's bouncing between like negative 0.25 and maybe 0.5. This is kind of like a common range for our parameter values. But we can see this a little more obviously if we go look at our histogram. Sorry, it's having trouble like showing all of these plots with a million samples in them, because my computer is very slow, my laptop. Okay, so this is exactly what we want to see in a histogram. So for Markov chain Monte Carlos, it's a little bumpy, but that's, you know, that happens with Metropolis Hastings. So basically, when we see this, we see that we actually have something like a normal distribution for mu, and this is the posterior distribution. This is like what your understanding of the probabilistic relationship between mu and your model. So if I wanted to understand what the average mu was, like what mu was on average, what my expectation should be, I just take the average of all of these samples, and I should get something basically like this, which is like I don't remember what it was, 0.16, something like that, which is not too far from the true mean of 0. Okay, so these are probability distributions and not point estimates. If you were going to do the maximum likelihood estimate here, you'd basically take this peak here, which would be the mean. But we have all of this extra information about our model where we get basically uncertainty, parameter uncertainty for free. And that's really, really important. That's the nice thing about Bayesian methods, is that you understand the totality of the distribution of your parameters rather than just the point estimate. And there's ways you can try and understand your uncertainty and maximum likelihood, right? If you take like the information matrix, you can use that to like get something like standard errors, more or less. But that is essentially a normal approximation to your parameter. And you may not have normal posteriors, and like it's pretty hard to find normal posteriors unless you have very, very well-defined models. Like OLS is nice. Okay, so these are draws from the posterior. All these 1 million samples, once you have this fuzzy plot, this caterpillar plot, all of those are distributions from the posterior. So you can take expectations, you can just calculate numeric values, and if you want to calculate the variance of some parameter or the expectation of the parameter, you just calculate the actual sample variance and mean of those parameters. You don't have to do any of this like really hard math, or sometimes very hard math that you might have to do if you were working in like conjugate priors, or you had like a very complicated model with like some weird interactions. You just like calculate them and then do whatever you want to with those parameters, and they are all drawn from the same conditional density. Okay, so you can just calculate the mean and the variance, and it ends up being incredibly slick. So this is actually the mean of the inverse gamma. This is the mean of the variance guess. So it's just a little bit shy. It's biased downwards. So the true variance was 1, but it's guessing like 0.9 on average. So these are point estimates for the variance, but point estimates are whatever. Okay, so this is a very basic example of how to use Metropolis Hastings and like how to write like your own log joint and kind of roll it and look at some basic examples.
Cameron, can you talk about some downsides to plain MCMC?
Yeah, one, it's slow. It can be slow. 2, it can be a little. It can be. Do you mean plain MC like in the context of like writing your own log joint?
Yeah, I'm just saying the way you presented it, you should always use MCMC. Is there any reason why you wouldn't use MCMC, or why you would need to do something fancier, like probably what you're going to show us now?
Sometimes it can be very, very tricky to get Markov chain Monte Carlo to work. It is often very finicky. So if you have a model that has a very complicated parameter geometry, there are a lot of you have to pick like very specific samplers, or you have to do a lot of tuning. So it requires a lot of work for you to get these estimates. if you have things that are like, this is a super well-behaved model. Everything I'm showing here is a very well-behaved model. If you have like linear models, Markov chain Monte Carlo works really well. If you have like some quadratic stuff, it's okay. But there's like a whole class of very complicated models that it's almost impossible to do Markov chain Monte Carlo on, just because you never reach this caterpillar plot stage.
So in particular, you keep trying to take draws, but your model is so complicated that your draws just get rejected all the time. And it's very, very hard to get draws that actually get accepted so that you can have a posterior.
Yeah, so they get rejected all the time, or there's heavy autocorrelation in your draws. And so it's entirely possible that you just never actually get true posterior estimates or samples drawn from your true posterior, just because it takes too long to get there. There's a lot of things you can do, but in my opinion, it's like for reasonably complicated Markov chain Monte Carlo methods, you need to spend a ton of time like really digging into stuff, and you need to be like kind of reasonably well informed, and it's not for everyone. But if you have very nice simple models or reasonably simple models, then Markov chain Monte Carlo is like kind of excellent.
Yeah. I mean, you're still kind of talking about, you're mixing in vanilla Monte Carlo, MCMC with other stuff. In my experience, things that you can do with maximum likelihood, you can also do with simple MCMC, and things that you can't do with simple MCMC, you probably also couldn't do with something like maximum likelihood, because your likelihood estimate, the reason that MCMC or even fancier Monte Carlo methods fail is that it's very difficult to sort of traverse the likelihood function. To get traverse the posterior using the likelihood function, because it's so complicated. And in those cases, if you're trying to just like plane out, get a local a global optimum through something like MLE, you would almost inevitably get stuck.
Yeah.
Because you don't have this like nice monotonic gradient or something like that you could follow. And so if your life is being difficult with MCMC, the answer is probably not to do vanilla MLE, but rather maybe to think about either simplifying your model or using some of these more fancy Monte Carlo methods that are sort of geared towards smarter traversing.
Yeah, that's a very good point. Maybe a counterpoint is that sometimes your likelihood is like only very well defined in kind of a small region. And because like Bayesian methods can have a very large exploration space. Actually, there's this kind of a two-sided coin. So one advantage of priors is that you can basically smush your parameters into a region that where your likelihood is probably likely to be well-defined or fairly smooth. And so when you're rather than run like maximum likelihood estimate with like hard bounds, you can have this kind of smoothness about where it is that your likelihood is reasonably well defined. And so it can kind of help you like help you do exactly what you said, which is not have to do this like global optimum thing where you're working with likelihood that can be very poorly behaved.
I'll say also, I don't know, the different communities talk about different things, but one of the things that Monte Carlo methods have developed a big following for, at least, is thinking very carefully about how you parameterize things, because you're so aware of how difficult it is to traverse the likelihood. You very quickly see if your draws keep getting rejected, you can figure out where that's coming from and find a better parameterization. And sometimes like the speed up and feasibility of a model with one parameterization versus another is like night and day. But it's very, very difficult if you're just trying to get, optimize a flat objective.
Yeah, there's a lot of weird magic that comes up in Markov chain Monte Carlo, which is really frustrating. Like there's a lot of folk knowledge about it. And that can be very agonizing if you're like kind of new to it, because you don't like, who do I talk to about the folk knowledge? Like, where is it? Is there a book somewhere that has this? And sometimes there is, but a lot of times it's like, you just talk to some rando and they're like, oh no, do this. You people. Okay, I think before I launch into this section, we should pause for like a 5-minute break. Okay, so when we left off, we just did conjugate priors, and we came back from the break. And so now I'm going to talk about this, something much more fun and interesting and very good at, this is a fun new tool that I feel like economists are like, don't know about a whole lot. And I really wish they did, because it's really fun and it's very interesting. And it's such a good way to understand some kind of economic concepts in a very flexible way. So probabilistic programming, you'll note that, we wrote out this log joint before, and it was incredibly painful, right? It was like, it's really ugly. If we had a lot of priors, we'd have to track them all individually. And this is like just really complicated. If you have a very large model, it can just take a long time to write out the log joint. And so that's a huge problem, especially if you're iterating on a bunch of model designs. Like if you're, in Bayesian models, you tend to have like less standard models. You tend to kind of custom design one for your specific case. And you might be like, oh no, I needed like some unconditional mean there, or I needed this to be like multiplicative or something. And you don't always, you want to be able to iterate quickly. And so writing out a custom log joint is a pain. So we have a better tool for this, which is called probabilistic programming languages, or PPLs. And so PPLs let us like specify a probabilistic model and then run inference on those models very quickly and easily. And in some cases, we can write models that are very, that look like something we would sketch out on paper. And we don't have to do a bunch of like hand math to derive some kind of like log joints. We can just like let the computer do it for us. And so there's a lot of PPLs. There are a great many probabilistic programming languages. And Julia itself has a ton of them. So I work on Turing.jl. I've been working on Turing.jl for like 3 or 4 years now. So I'll show you how to use that. But I just want you to know that there's a ton of different PPLs that have a lot of different fun and interesting tools. So like even in just Julia. So there's Sauce and Gen and Forney Lab. These are all like fantastic, well-written tools that you should poke around. And there's also ones that are in other languages that are extremely robust. Like Stan, for example, is like a very popular, very good tool. There's just a great many others. I'm not going to go list them all, but I'll walk you through Turing, and then this will expose you to probabilistic programming languages, and then maybe you'll find one. Maybe you'll like Turing, or maybe you'll go find one that fits your needs a little bit better, or is different at something, better at something. So I'm going to sketch out a really basic Turing model for you. So first, we're going to start by importing Turing. So using Turing. So if you don't already have this, you have to do add Turing in the command line. Or import pkg, pkg.add Turing, if you don't already have it. And then Turing exports this at model macro. So you put at model right in front of a function, and it'll go through and reconfigure that function as if it was a probabilistic model. So I'm gonna call this function gdemo, and it's going to accept some value, some x's. This is going to be a vector of random draws from some normal distribution. So up here, I'm going to create some priors. So I'm going to use s tilde, right? This is just like probabilistic notation. And then I'm going to say s is distributed according to inverse gamma 2, 3, right? So this is a very wide parameter, a wide prior on variance. And then I'm going to say m is normally distributed according to 0 with a variance of square root of s. This is a standard deviation. This is a variance parameter. This is standard deviation. And then I'm going to go through and calculate the likelihood. So note here that s and m don't exist anywhere else, right? They're not like arguments or anything. So these are freshly created. So when you do this, this is drawing these as if they were parameters. These are now parameters. S and m exist as parameters. And then we're going to calculate the likelihood. And we're going to go for each element inside of xs. I'm going to say xsi is distributed according to normal m square root of s. xs here does exist. It exists up here. xsi is defined, right? It's some value. And so when we do this, this is actually accumulating the likelihood. So everything that's basically happening in this model is we're going to draw our parameters, get the log priors for S and M, given some random draw of S and M. And then we're going to accumulate the likelihood, the log likelihood of this, conditional on M and square root of S. Okay, so this is just like a nice short and sweet model. And you can write most Julia code in here. There's like a lot of, if you get into more complicated stuff, there's a lot more things you have to do. And if you're writing like a complicated model, then just like email me and I can maybe help walk you through something or point performance stuff out to you, things like this. But this is a very basic model. You can go to turing.nl if you want to learn more complicated stuff. So we have our model. And so we're going to generate some random data and pass it to that model. So in this case, I'm going to start with some data is just going to be normally distributed with a mean of 15 and a standard deviation of 2.2. And then I'm going to draw 30 random variables. And then what I'm going to do is I'm going to create a model and I'm going to call gdemo with data. And you'll note this I've left this thing here so you can see what it actually returns. And it returns a dynamic PPL model. So this is like a very gnarly, kind of ugly looking thing, which is the result of compiling the model. So our model is now compiled and ready to have inference run on it. If we wanted to, actually, no, I'll leave this on for a side, but that is there now. Now I'm going to do the exact same call that we did with advanced MH. They actually use the same interface, which is a fun thing to write. Thank you to David for also doing that with me. David's the best. David Widman, he's amazing. Everyone should hire David. So basically, I'm going to pass my model here. And then I'm going to use MH. So MH is a function exported by Turing, which constructs something. This ends up actually calling Metropolis Hastings. And then I'm going to give it the proposal kernel, which is just going to be a diagonal matrix. This is just the identity matrix. So this is basically the same as what we did before. Then I'm going to use MCMC serial, which is saying I would like to sample 4 different chains. All in serial. I don't have multiple threads or anything. I'm going to have 10,000 samples in each chain, and I want 4 total chains. So when I run this, and it spits out the summary statistics here, we can see we have 10,000 samples. We have 4 total chains. It gives us some statistics on computational time. So wall duration is start to end. Compute duration is how much time was actually spent computing within a chain. So compute duration can be significantly larger than wall duration, for example, if you use multiple threads. And we can see the mean here, right? So the mean of M is 14.48. So that's pretty close to our true mean of 1. And it has a standard deviation of 1, which is like, is that right? I don't know if I'd expect that. I think I would expect that. And so, this is just a nice way to get a bunch of chains. And the reason we sample multiple chains is that, I'll talk about this a little bit more because I don't think I have a slide on it. It's usually a good idea in Markov chain Monte Carlo to sample multiple chains. And the reason that you should sample multiple chains is that Markov chain Monte Carlo can be very sensitive to starting points, particularly for like really ugly models. So what you want to do is basically pick a new chain and put it at different spots, random spots. And then the idea is that every single one of those chains should converge and line up on top of each other. And if they don't line up on top of each other, your model has not converged. It's like, those posterior samples are probably not going to be very good because the Markov chain has not been run long enough. You need to increase the number of samples or maybe consider reparameterizing your model to make it a little smoother. So I'll show you an example of what this looks like. So you can actually just call plot on your chain and it'll put trace plots on the left and density plots on the right. So this is exactly what you want to see when you run multiple chains. So there's actually multiple colors in here. I know it's a little difficult to see. There's like purple, green, blue, and orange. When they're all on top of each other like this, that means we have this is each one of those each color represents a different chain. The fact that they're all on top of each other means that this model is like fairly well behaved, and we have enough samples, and like we converge to a stationary distribution. And you can see on the right-hand side, the densities show us our posterior distributions. This is basically, this is proportional to the log PDF or the PDF of our posterior parameters, posterior density of our parameters. Okay, but you'll also note that there's like some weird stuff going on here, right? There's like really fat tails. And you can see exactly why, right? Because our prior was basically that the mean was 0. Right? So it randomly initializes around 0. And then it very quickly jumps up to where the more likely region, which is around 15, which is where the data is centered. So this is common, the early part of a chain is typically discarded, right? This is often referred to as burn-in, where it takes a little bit of time for your Markov chain to get to a region that is like kind of a normal one, which is around here. This is like something like the typical set. This stuff is all kind of burn-in. So I would kind of discard that stuff. And the way I can do that is I can just specify the number of iterations I want to do. So if I give MH chain, I just pass in a range to the index, it'll give me a smaller version of that chain, and then I can replot it. And now I don't have these weird fat tails, and this is something a lot more reasonable. And you can see when you look at these chains here that these are all caterpillar plots. They're all on top of each other. This is something I really like to see. Like this is like a pretty damn good sample of Bayesian models. Okay, so this is called discarding the burn-in. So this makes it so that when you actually calculate values with from your posterior, that you end up having really nice things. Okay, so Turing has a bunch of inference algorithms. Some of them are Markov chain, some of them are particle sampler, particle methods. Some of them are like importance sampling, which I don't work with importance sampling. I understand it's like kind of a weird, bad idea. We have better tools now. But basically you can use MH for static and random walk Metropolis Hastings. This is like really basic. If you don't have if there is no gradient for your model, or you have like mixed discrete and continuous variables, and you don't want to think too hard, Metropolis Hastings works. Like Metropolis Hastings works for literally everything. Like that's the really nice thing about Metropolis Hastings, even if it's fairly slow to converge. If you have continuous samplers, you can do HMC, so raw Hamiltonian Monte Carlo, but you have to tune it. You have to give it some parameters here. So it can be, it can be a little finicky because you have to kind of like set how much it leapfrogs, and what the adaptation rate is, or the step size. Or you can just use nuts. And nuts is basically a thing that like looks at your model, it tries really hard to understand the shape of your distribution, and then it gives you a value, it gives you a version of HMC to run. So nuts is like a kind of an automatic push button inference tool, is commonly how it's described. And it's gradient. It's a gradient based method. You can also combine multiple samplers in Turing. This is actually a really fun part of Turing, where you could do nuts for your continuous parameters, and then you could do like particle Gibbs for your discrete parameters. And then you can kind of mix sampling, and you still get Markov chain Monte Carlo without having to reparameterize your model to be all continuous like you might have to in nuts. So there's all kinds of like sampling tools in here. Also, elliptical slice sampling is very cool, and I don't get to use it enough. So there's lots of stuff in there. You can see that all on Turing.nl. Okay.
I should say this is very cool. And I've seen a lot of different kind of languages for sampling, but it's very rare to find something that can do both nuts and Gibbs or whatever.
Yeah, they're like, that was one of the reasons I think like that was like the very early like super big important feature about Turing was that you could do compositional sampling, where which is like a kind of a pain in like Stan, for example. Like Stan, you kind of have to have continuous parameters. I know I think they're working on like some automatic marginalization stuff, but it's it's still kind of a pain. This way you can just sample discrete parameters very well. So if you work in like state space models, it's kind of nice to, or like hidden Markov models, it's really nice to have like states, which are discrete, be kind of imposed. So it's a very cool.
You don't have to marginalize over discrete variables.
Yeah, which is a huge pain. I don't like doing it. It's too much math. I don't do math.
It can be a real pain. I have a question. So one of the
Sure.
pain points I've often had with probabilistic programming languages is that in economics, we often have models that have fixed points as part of them.
Mm-hmm.
So, you have a bunch of parameters, but you don't just have a clean transformation like, a log normal of some parameter that you're trying to figure out. Mm-hmm. Instead, you have some parameters that go into some first order condition or something like that you need to solve numerically.
Mm-hmm.
How does Turing interact with those?
So I guess the question is more about, is the fixed point with respect to the true posterior distribution of the parameters? Or is it simply a likelihood? So conditional on some parameter draws, I can calculate the likelihood, which is a function of
it's the latter.
The
fixed point is part of determining the likelihood.
Yeah. Okay. So in that case, Turing doesn't care. Like that's a computational thing that you're doing. The only time it can be a bit of a pain is if your fixed point operator, like you should know. It would be nice if you knew the gradient at the fixed point.
Yeah, so that is always the trouble, isn't it?
So that's one way. That's one thing that you kind of need to do. If you don't have that, you can use any of the other methods, Metropolis Hastings or particle Gibbs. Those are all perfectly fine ways. If there is no gradient that you can define or that cannot be calculated using automatic differentiation for the fixed point operator, you have to use one of the other methods. But Turing shouldn't care, right? It's just part of the likelihood. So it's kind of a black box in that sense. It's just I give you some parameters, you give me a number. But yeah, those are fun tools. I haven't found like a good example of this like kind of fixed point operator with like a Bayesian thing. I know that it's like a BLP thing, but I need to like roll it up and actually type it up.
I have lots of examples. I actually know a friend of mine from the Stan team, I think, wound up developing a bunch of tools for Stan based on some of these like nasty econ problems.
Oh, cool. I'm into that. I feel like I need to like tinker around with them because it was nice to. I like fixed point problems. They have like a nice.
I think it's not just in economics that they show up. I think there's a lot of this kind of stuff that shows up in physics and like particle dynamics and things like that too.
Yeah. Okay. Here, I'll step into this. Oops. Let me rerun this. Why did I do this? Why did I do this to myself? Okay. So I'm going to show you how to use nuts because nuts is an extremely good tool. So nuts converges quickly, and by converges quickly, I mean you need a far fewer number of total samples relative to for example like Metropolis Hastings to get a very smooth understanding of your posterior. So I'm going to do the same thing. I'm going to sample 4 chains in serial. And then I'll plot it out so you can see what it looks like. Get any divergences? No divergences. Anytime you're using nuts, if you see something that says you got a numerical error in Turing, or if you're in Stan, it says like divergences detected. That's an indication that you may have like some problems with your posterior geometry. And there are many tools for dealing with divergences. I'm not going to discuss them here because they're like kind of complicated, but it's like it's a thing that's important for you to pay attention to in nuts because it may invalidate some of your posterior. Okay. So here is the posterior plots. You'll note here they actually start at 500, not at 1. And the reason is that the way that nuts works is there is an adaptation phase. So the first number of samples, some value you can specify it could be like 500 or 1,000 samples, is where nuts is just kind of going crazy. The whole point of it is just like bouncing all over, trying to understand the shape of the posterior density and particularly the covariance between your parameters. And so while it's doing that, it's generating the parameters, the parameters it draws are mostly garbage. So we basically cut out the adaptation phase. The nice thing about that is, when your chains start, they tend to start nicely. So these are all what I would consider converged. There's like a little bit of an interesting estimate here. I'm not sure what's going on there. But we can also see our density plots are relatively smooth. And we only, I got 4 chains very, very quickly. And all of this was actually calculated with automatic differentiation for free. That's the nice thing about Turing, is like if you use nuts, it'll just calculate the gradient on your behalf if it's easy enough to do. Sometimes you may run into some issues. But this is a good plot. And so I recommend nuts if you have continuous parameters, or some combination of like Gibbs and nuts if you work with, or like Gibbs with nuts and like particle Gibbs or something if you have some mixed discrete parameters. That's on the website. I'll like Turing.ml if you want to go see that. Okay. So you don't, a lot of the difficulties I think that people have with Markov chain Monte Carlo is that it isn't quite as hard and fast as frequentist stuff. You kind of have to squint a lot. You have to take a lot of the interpretation, the role of interpreting your results on your own shoulders. Like you don't have a lot of like really nice, well-defined tests that have like asymptotic assumptions that you meet. You basically have this like very fuzzy, is this chain good enough for me? And so you have to kind of take an artistic understanding of your statistics almost. So if your chain is not converged, right? You do not have a valid set of parameter draws. You can't just like take the mean and say, oh, okay, this is like the mean of the posterior. It's not done yet. You need to let your chain run. And so there's a couple of ways to check for convergence. There's actually a lot of ways, but I'll give you a small sample of ways. So the first one is like what you should do anytime you do any kind of Bayes stuff, any kind of Markov chain Monte Carlo. Look at the trace plots. Do they look like caterpillar plots? Do they look like this? If they look like this, you can start thinking, oh, okay, I think it's converged. Or at least it's in a region where it's converged. You should not be seeing a whole lot of jumps. I mean, you can see jumps, but they should jump to like a stationary point. You shouldn't see like trend lines or autocorrelation. Those are all not good. So, look for these caterpillar plots. You should also look at your R hat. So R hat is a value that's calculated, for example, in your display chart. So you should look here on the right-hand side when you look under R hat. If this value is close to 1, you have like reasonable confidence that your chain has converged. And if you're using R hat to diagnose something, make sure you run multiple chains. This gets a lot more informative if you have multiple chains. Don't just use like R hat and like run one chain and say R hat's close to 1, I nailed it. Like actually run multiple chains. So Gelman in Bayesian data analysis basically notes that less than 1.1 is pretty okay. So as long as your R hat is like, around 1, less than 1.1, you're probably okay. But again, it varies with your model. Is the effective sample size, ESS, relatively high? So this is like, you can think of this as like, how many actual like, of the 1,000 samples I ran, how many are like reasonably okay? How many contained new information? And you can see this is an output. If you display your chain, it'll tell you, okay, of the, of 4 chains across 1,000 samples, so 4,000 total samples. For M, about 3,200 were like good samples, like high information content samples. So this is, this is kind of an indication that we did actually pretty good. If you see 60 here and you sampled 40,000, 4,000 parameters, but your ESS is 60, your chain needs to go longer. You don't have enough. That's a really, really low rate. So, but again, it's, there's no like hard and fast rule here. You have to be like, does this feel correct? And then there's other ways that are more complicated, but R hat, ESS, and trace plot checks are pretty good. There's some, miscellaneous diagnostic tests that are good. You can look those up. There's like, yeah, there's just a bunch of them, and you'll kind of need them as you like look around. And if you're looking at your trace plots and your trace plots look a little weird, you may need to look into some other diagnostics, or just run your chains longer. Okay. So now we're going to get into the fun part here. So I'm going to show you how you can use probabilistic programming to work within the context of an existing economic model. So you can see how kind of like flexible it is and powerful. So I'm going to put us in this world where we're going to do a little bit of auction theory stuff, and it's okay if you're not like super auction theory-y. I'll give you like a nice little demo. But the important thing here is to see how it fits into this model. Like first price single unit auction, for which we have data on 5 risk neutral bidders, and we're only going to do one auction. We only have one auction and 5 bids, and we're going to have this data. And sorry, let me stop for a second. Bidders place bids to purchase a good, and the highest bid wins the item. Right? That's super simple. That's first price. And we want to understand the parameters that govern the bidder's private valuations. So if we assume that all these bidders have valuations for this good that are drawn from the same distribution, maybe we want to understand how much they care about that thing. And if we understand the distribution of how people care about a good, how they're distributed according, how their valuations are distributed, we can do a lot more interesting stuff, right? We can do like counterfactual analysis or understand some kind of welfare problem or whatever. I'm going to leave that off to the side here. I'm going to focus on just estimating this valuation distribution. So this is adapted from Hubbard and Parsh, and I expanded it a little bit. And Shosh helped me understand this a lot. So like applause to Shosh for like sitting down and like walking through these with me, because these are very fun little examples. Okay, so we see each person's bid, BI, and we want to know the distribution of private valuations, VI. And VI is drawn according to some distribution we don't know, and it's on these bounds between V lower bar and V upper bar. So valuations are not known to us, but we want to model the system to infer what those valuations could have been, right? So we observe people's bids, and we know that those bids are probably functions of their valuations. And once we observe those bids, we can kind of back out what their valuations were and then try and parameterize the distributions from which they came. Okay, so this is going to be the important task we have here. So the way this, I'm going to very loosely sketch out this model. So if you want to like more detail, go check out the Hubbard and Parsh thing, because it's a very good little handbook chapter. But bidders are going to have this ex ante utility from a bid, which is basically given by their valuation minus the price they paid, the bid, times the probability of winning given that bid. So they're going to pick a bid to maximize this ex ante utility. There's a shared best response function. So I'm just going to assume this because everyone has the same, their VIs are all drawn from the same valuation. And this best response function, sigma, basically just takes your private valuation and returns a bid. So this is a function we don't know, but we know that it's strictly increasing, continuous, differentiable, etc. Right? This is like a nice, well-behaved function that everyone understands because it's an equilibrium function. And then we're going to define this inverse bid function, which is just the inverse, sigma inverse, and that's going to give us psi of your bid. And so psi, this inverse bid function, tells me what your valuation is given your bid. Okay. All right, so that's fairly standard. And the inverse bid function will come up in a second. So your win probability, this is the part of your ex ante thing. We want to work through this for a second. It's basically just the probability that everyone else's bid is lower than yours. So this is a joint probability, so I multiply everything together. And what I'm going to do here is I'm just going to invert this probability here. So I'm going to say, all right, what's the probability that everyone else's valuation is less than my inverse bid function at my bid? And we know that that's actually, you can just work through this. And this is just the same thing as the cumulative density, the CDF, evaluated at my own, oh, sorry, this should be BI. Evaluated at my own bid times to the power of n minus 1, right? Because that's the number of other people who are bidding, right? So this is the probability that everyone else has a valuation lower than my valuation. Okay, so this is just a nice simple little identity here. Okay, and then we can rewrite the payoff function here, the expected utility, as my valuation minus my bid times the probability of winning, which is given by this CDF. Okay, So when we take first order conditions of that ex ante utility with respect to the bid, we're going to get this identity here, which is some kind of gnarly math, which we're going to, I don't want anyone to focus on too much, except for this part here, right? Which is basically the derivative of our inverse bid function. Wow, I just like put VI everywhere in the inverse bid function. Wow, I'm so sorry. So the derivative of our inverse bid function with respect to the bid. This is going to be important. We know that by the inverse function theorem that the derivative, that this relationship here is equal to this, right? It's just the derivative of the inverse bid function is equivalent to the inverse of the derivative of the bid function with respect to the valuation. So we can just sub it in. And when we do that, we end up getting this differential equation here where the bid function, which is the thing we want to know, right? We don't know this bid function. We're just going to plug this in here and then calculate, what the derivative of your bid function as a function of the level of the bid itself. So this is it called a first order differential equation? Is it first order? Something, I don't know. Whatever. It's a function of itself. It's a function of the integral of this thing. Okay. So the nice thing about this example is when everybody comes from the same distribution, there's an analytic solution to this. So the analytic solution to this differential equation is basically just your own valuation. You should bid your valuation minus the ratio of the integral of the reserve price. So the reserve price here, actually, I can just rewrite this as V, is it underline? Yeah, so you know that the person who is the lowest valuation, they're always just going to bid their valuation. They make no profit at an expectation. So they're always just going to bid their valuation. There's no reason to bid more because they'll never win, and there's no reason to bid less because then they lose. They still want to bid a little bit more. And so we're just going to integrate from the worst possible bid, V underbar, to your own bid. And this will be just the, we're integrating across the win probability here. And then we're going to divide by the CDF at our own point to the power of n minus 1. Okay, so this is going to be our bid function. All right. So what I'm going to do is I'm going to import a package called QuadGK. So this is Gaussian quadrature. So this is how you do numerical integration. So this is an extremely good package. QuadGK is like very fast, nice and easy to tinker with. Numerical error is like quite low. It's really, really nice to use. So if you're going to do any kind of numerical integration, which is what we're going to need for this part right here, this numerator, I'd recommend QuadGK. There's some other ones, but QuadGK is really good. I'm going to set a seed just so I have the same bids every time I run this. I'm going to specify 10 bidders. Actually, let's keep it at 5. And then I'm going to specify, I'm going to place a parametric assumption on the distribution of valuations. I'm going to assume that they're exponential. So the exponential distribution is kind of shaped like this. I'll show you an example a little later, but it has one parameter, which is just lambda. And in my case, I'm specifying that the true lambda is 2.5. And then I'm going to specify lower and upper bounds on the valuations, where I'm going to say, all right, everyone bidding in this, everyone has at least 0.1, and nobody has a valuation more than 15. And then I'm going to construct a truncated exponential distribution that goes from V lower to V upper. And then I'm going to draw some random values for the valuations. So we see somebody here has a 9, a valuation of 9, and then this person down here has a valuation of 0.13. Okay, so these are the valuations for the bidders that we're going to work with. These are the people who are participating in their bid, and this is what we would know about them if we could, just ask them. So I'm going to write down the analytic bid function here. And I'm actually going to plot this out in a second. I didn't write a function to plot this, but I would like to. So the analytic bid function here, let me zoom in a little bit. oops, just accepts, it's, you know, I'm using sigma here to match the notation. It accepts some valuation of an individual, a guess about lambda. This is, this will be important later when we get into Markov chain Monte Carlo, where we can change our guess about what the distribution of valuations is. V lower and V upper, these are just used here in creating the truncated distribution. And then N here is the number of bidders, total bidders. Then I'm going to find a function here, which just is the CDF of the truncated distribution, of the valuation distribution to the power of n minus 1. And then I'm going to calculate the numerator here. So quad GK, right? This is just going to integrate this function f from V lower to V. That was the thing I just showed above in math. And then the denominator is just this f function here evaluated our own valuation. And then I'm going to return V, our valuation, minus the numerator divided by the denominator. You'll note here I'm doing a tuple unpacking thing here. This is because quad GK, when it calculates your integral, it returns your value, the integral value in the left-hand spot, and on the right-hand spot, it tells you what the numerical error was. So I don't care about the numerical error here. It's, you know, it's going to be relatively low for this problem, but you may want to keep an eye on it if you're doing a lot of like really tiny integrals. And then I'll just store all this stuff in a nice little data frame. Okay. And I actually want to plot this out. So I'm going to do V lower, V upper. Let's do like 100. And then I'm going to map. I'm going to calculate all of the bids at that point. Okay, and I'm going to plot BS plot, bid plot, so we can see what the actual bid function looks like. This is what I want to show you. So on the bottom here is what your valuation is. So for example, valuation of 10, what you would bid is like 4.75, 4.8, something like that. Okay, so yeah, that's an example of what the bid function looks like. So you can see. Alrighty, I'll skip past that part. Okay, so pretend now that we don't know this true parameter lambda 2.5. This is the thing we want to know. I think, is this the thing that nerds call the S-demand? I don't know. We'll see. But we want to infer from the bids we observed what lambda is. And so I'm going to set a prior that lambda is equal to 1. Like I'm just going to take a guess. I don't know. I don't have a good sense of what lambda should be. And so let's take a look at how my prior looks as compared to the true density. So this is an example of if I knew the true density and I knew the prior, this is what they would look like in comparison for the valuations. This is the PDFs. I definitely overweight, my prior definitely overweights mass towards the beginning. So I basically overweight the proportion of bidders who are very low valuation, and I underweight higher valuation bidders. So this is kind of how my prior tilts things towards trying to make guesses about there being a lot of low value bidders. Of course, we don't know the true prior or true posterior, so this is kind of, or the true value. So this is kind of a I just wanted to show you what it would look like. Okay, so let's write this up in Turing here. So both alpha and beta have to be positive. So I'm going to use the prior that they're going to follow a truncated normal distribution. Oh, sorry. This is set up when I was using the gamma distribution. Yeah. Okay. Whoopsie. So basically what I'm going to do here is oh, and I was testing something and I didn't go back and do it. Okay, so lambda here, it has to be positive. So I'm just going to use a truncated normal distribution with a mean of 1 and a variance of 3, and it's going to go from 0.01 to inf. The reason I set it at I put the lower bound at 0.01 is basically working with like parameter values that are at 0 or like extremely close to 0 is kind of problematic. So I just kind of want to cut that out of my region. I'm just taking a very strong stance that it can't go below 0.01. And then I'm going to have this parameter thing, this variance parameter, which is how tightly bids, I believe, bids adhere to the calculated bid function. And the reason I'm doing this is because I'm kind of allowing for noise in how it is that I observe people's bids around the estimated bid function as a function of lambda. So this is just kind of a trick to make this probabilistic, because if I allow for the calculated bids to be strictly deterministic, there's essentially one this whole thing, it becomes a very peaky problem, and it becomes really hard to do inference on. So having this variance parameter and assuming that I'm observing bids with a little bit of noise ends up making estimation a lot easier. And then I'm going to draw valuations here. So V, this is actually going to be a vector. I'm going to use this fill dist function. And then I'm going to use exponential. This should actually be truncated exponential lambda. V lower, V upper. And then I'm going to replicate this array num bidder times. So VI is, I'm going to have, for example, if num bidders is 5, I'm going to have V is going to be 5 parameters in a vector. And then I'm going to calculate the bids for each of those bidders using the best response function and the provided lambda. And then I'm going to observe the likelihood of getting those bids conditional on the calculated bids that they should have bid. So this is data. This is what I'm predicting. Okay. Alrighty. So let's see what it does. I'm gonna specify my model here. I'm gonna give it the bids I observed. I'm going to specify 5 bidders, and then I'm going to give it the upper and lower bounds. And then I'm going to use nuts here. And you'll note that it uses forward diff by default. If you're working in a model where you need to do, if you have a lot of parameters, you can do Turing.setAD backend reverse. Okay, so if you want to do this, if this is one way. If you want to switch to the reverse diff AD backend when you're using nuts, that's one way to do it. Okay. Alrighty, so I'm going to run some inference on here. I'm going to sample 4 chains. I'm going to use multi-threading this time. And it'll take it a second here to compute. This is like both the annoying part and the fun part of doing any kind of Bayesian inference, is because, you know, a lot of times you'll end up running these models and they end up being kind of a pain. So you wait and kind of sit and spin in your chair and, you know, find fun stuff to do. I want to point this out here. When you see warning the current proposal will be rejected due to numerical errors, this is because we've gotten a divergence, because it's very difficult to calculate. Like there is something about my posterior geometry that is a little ugly, which I believe is coming from the truncation and the valuation distribution. This could mean that some of my samples are invalid. And so when I calculate the summary stats here, I can see that the lambda I'm estimating on average is 0.293, which is higher than 2.5, right? But this is the mean. So I want to look at some of the actual like median and percentiles. So for example, I see actually the median estimate is 2.7, which is pretty good for 5 bidders, that I can infer that the median is relatively close to 2.5. And it's completely far away from our prior, right? Our prior was like centered around 1. So we've done a pretty okay job at inferring what the lambda is, at least on the median perspective. Our posterior is quite wide, looking at the 75% range, but still on average we're doing pretty good. So I plotted this a little bit so you can see what it looks like. These are histograms. You'll note that they're actually different sizes because I haven't normalized them. Remember that all of these are only proportional to one another. So you actually have to scale them up or down to meet, just because, because we're not using the normalizing constant in Bayes rule. The ground truth is right here, and the exponential is always is pretty well centered around the ground truth for each of the 4 chains. Okay, so we can be like reasonably confident that, at least on average, the valuation distribution has a mean of 2.5. I also wanted to look at, this is Tosh and I were talking about this during the break, but I wanted to see how well this model does at inferring the individual valuations, right? Because if you look here, they're treated as parameters, right? I have posterior distributions for the first bidder, for the second bidder, for the third bidder. They're treated as parameters in the way I've specified the model. And I want to know, like, was I inferring them correctly? And the answer is no, I'm not. Like, they tend to always be the same. Actually, here I can add bids. So we can see what that looks like too. So like, even though there's tremendous variation in bids, it's having a very hard time in finding variation in the average estimated valuation for individuals. So this, I suspect, is, need to have a lot more data or repeat data, and just kind of a bigger panel to evaluate things on. But this is something I like tinkering with. And this is the kind of thing that you can do where you can say, okay, well, if I treat people as having parameters, what, bidders as having parameters, what would they have done? Okay. So I would conclude here, generally a good exercise. If we scale up the data, we'll have much tighter estimates of the true lambda, but we've done our best and we did a pretty good estimate. Okay. That's it. That's all I got for you folks. Yeah. Any like wrap up questions or anything? Okay. Excellent. All right. Have a wonderful day, folks.